Yeah, hi, good morning. I apologize for not being there as well. I'm not as brave as Gianluigi is. And I really want to thank you for this opportunity. I spent most of my career abroad, and so it's really interesting for me to see this very high-level research that is being done in the schools around the country. So I really learned a lot, and again, I'm sorry I couldn't meet you there in Lucca. So my title is Complexity Reduction Numerical Simulation via General Mesh Adaptivity. The idea is to give you a bit of an overview of what I work on. It's mainly theoretical numerical analysis with applications as well, but I want to just give you a broad overview first of all, to have an idea of indeed what is my research area. Is continuum modeling with PDEs, applying biomedicine mainly, but also other sciences. I'm interested in interaction of different phenomena like transport and diffusion and nonlinear effects, such like, say, modeling and simulation of flux through semi-permeable membranes. I develop numerical PDE methods and relevant HPC implementations, looking mainly at finite element type methods on general meshes and automatic adaptivity of these meshes through a posteriori error estimation. And that's really what the talk will be about today. Let me start with some motivating examples. Although we saw some amazing applications yesterday and today, so very complex problems where indeed complexity reduction is crucial, but this is probably the biggest problem I have ever been involved in, with is the simulation of the Earth mantle modeled by the Boussinesq system of convection. This is a truly convection-dominated problem where you have formation of layers that one would like to appropriately simulate, and this is just a simple example of how you have indeed very sharply moving layers that you would like to resolve, and the idea of mesh adaptivity as a way to achieve that. And indeed, in the case of the Earth mantle convection, it's only possible to get good accuracy if you do such a mesh adaptive approach. And the result of this work actually was put into, embedded into Aspect, which is one of the main code for this type of public main code for this type of simulations. And the interesting computation algorithmical problem here was to implement the load balancing operation that you would need to run these simulations in parallel when you have the mesh indeed granularity changes in time. This is another example of indeed sharp problems with sharp layers, such as a Lotka-Volterra reaction diffusion system. Again, the idea is that you really need a local resolution, and I share here at the top right example of a 3D mesh of that. This is standard 3D meshes, and the idea here was to say, well, can we do something more than that? And this is such an example in two dimensions using the virtual element method that indeed allows for general meshes. What you see here are indeed the mesh used. These huge polygons here, for instance, is truly the mesh that is used to simulate this system of 3 species that are mutually exclusive, so they tend to have very sharp layer between them. So it's a very good toy example. What if the complexity comes from the geometry? This is such an example of a bone scaffold made of 3.2 million cells. So running, say, a simulation here may be prohibitive. So the idea is that we would like to somehow upscale the model without losing the resolution of the geometry. And we can do that by agglomerating the voxels that compose the geometry given by MRI and into all these polyhedral elements you see here. So these are 4 elements given by the meshed model. So you retain the geometry, but you upscale in terms of number of elements needed, and you run your simulations. And if your accuracy is not good enough, then you can indeed do mesh adaptivity, so somehow refine back. And this is such an example here on a different geometry, but same model of trabecular bones. Again, you start with more than 1 million tetrahedral elements, you agglomerate them, and then you run a goal-oriented, in this case, adaptive algorithm, and you reach somehow a sufficient accuracy with still much less complex simulation. So overall, the idea is to design high order and geometry conforming PD discretizations of complex multi-scale domains. So you could have indeed configurations including curved or moving geometries, such as in, say, fluid structure interaction and complicated geometries. So the idea is to achieve this not can apply by applying. So the basic finite element method would use say triangular meshes and so on, and we're all used to those. But what about more general elements? And that's the idea of this approach, is to use non-standard finite elements, which would mean, say, more non-standard shapes, but also non-standard functions, not only, say, polynomials, because they could be more suited to your problem, say, for multi-scale models, and again, compatible discretization, compatible with respect to the physics, and indeed to the geometry. And for that, the idea is indeed the development of general element shapes. So your element is not necessarily a tetrahedra, but could be a curved polyhedra or a arbitrarily cut standard element. And the claim is also that this allows much easier automatic mesh adaptation. The main technology that I've been working on in this respect are indeed virtual element methods and discontinuous Galerkin methods that are indeed and 2 examples of non-standard finite elements that allows very easily the use of more general meshes, making indeed also adaptivity much more easy to implement because it's fully local. So the common feature of all these elements that they use physical mesh elements. The advantage of this is that they are robust with respect to mesh distortion, and indeed that they make local adaptivity easier. The cost of it is a higher cost on assembly, but I will. That's something I will come back in a second. This is an example to explain what I mean indeed with complexity reduction. You see here just a simple heat equation problem in 2D on a complicated on a domain with a complicated boundary. And the idea here is that somehow resolution can be achieved by general elements. So here, for instance, we use some polygons around the mesh, and perhaps raising the resolution by raising the order of the polynomials of the finite elements used, rather than somehow conforming to the mesh. So here, for instance, we see so left would be, say, non-standard mesh, and right a standard mesh. If you see here, the number of unknowns is halved by using indeed the higher order elements on the coarser mesh. Giving, although this would give you actually slightly better accuracy, essentially the same accuracy. So you have the same accuracy with potentially with, in this case, half the number of unknowns. So how do you do this adaptivity? Theoretically, you need you combine PDE stability with Galerkin orthogonalities essentially, and appropriate approximation error estimates to derive an a posteriori error bound. I'll show you an example in a second. And then the idea is that so these are posteriori error bound. That means an error bound that only involves the quantities that you compute and not the unknown exact solution can be used to drive the adaptive procedures. And again, general meshes will provide a more general flexible to do that. For instance, the issue of producing hanging nodes is completely solved in this respect. And so that's just to give you an idea of indeed what a posteriori error bound is. So on the left, indeed, you have the error between the exact solution U and the computed solution UH. And the idea is that we know that this is bounded by this quantity on the right that only depend on the computed solution UH, and is in fact made up of the local contribution to the elements K of the mesh. So that means that indeed we can also, by looking at the difference magnitude of these terms on each element, we know which element should be refined because more resolution is needed, the error is big, and those in which that should instead be coarsened. This is just actually a simple example that we cooked just to mention the fact that indeed the use of general meshes allows for very coarse, very aggressive coarsening, where the solution doesn't vary much, so there's no need for resolution. And just to arrive to show you how the error behave as you do these subsequent solutions. The whole point is that at the beginning, the presymptotic, more interesting regime you may achieve with this aggressive coarsening reduction of error at the same time as reduction of number of degrees of freedom, just because you are moving the degrees of freedom where they are needed. Probably, and well, this is just an example of my current one of my current projects on some cardiovascular simulations, working with some surgeons that treat so-called univentricular heart condition, which come from babies that are born with essentially only one ventricle properly pumping. So up to the 70s, this type of condition was considered inoperable, but since Fontan designed a Fontan circulation, which is depicted here on the right, indeed these children are indeed treated by diverting the returning circulation into away from the heart and directly into the pulmonary arteries to essentially create a single circulation given the single pump, and the study here is about indeed checking, optimizing the anastomosis of the inferior and superior vena cava into the pulmonary arteries. So starting with imaging, producing the model, and then testing different configurations of the anastomosis, and then kind of giving back the doctors, medical practitioners, the type of indeed numbers they want to look at to improve the results of the operation. I probably skipped that. I just wanted to say one word to, in a sense, reconnect also what with the end of the lecture by Roberto earlier this morning. As I was saying, there is a cost in the assembly of this type of more general elements. However, the modern computer architectures, and in particular GPU architectures, make this potential extra cost quite trivial. You see here the assembly of tens of millions of degrees of freedom can be made on GPUs in the order of a few seconds. So when this is done, then essentially the idea is that the systems you will have to solve will be generally smaller for the same accuracy. So really the assembly in principle is the bottleneck for this type of technologies, but thanks to the new architectures, these ideas somehow assume a new value. I'll probably stop here. I'll try to be as short as I could. It's just a quick summary. The idea is to do computational modeling of complex processes in a robust and way, and trying to achieve a complexity reduction through compatible discretizations and adaptive resolution. Related to this, there's interesting problems, of course, of parameter estimations and inverse problems and so on, and crucially the development of appropriate HPC algorithms. So with this I'll stop, and I'm happy to take your questions.
Thank you very much.